Hello guys, welcome back to my channel. Today I have a weird integral for you guys. Another weird integral. So let me give you a hint. Today there's going to be the polylogarithm that's going to be introduced. And as always, please stay patient throughout the journey guys. It's going to be fun and let's get to it. So to start with we have I, which is defined as integral from 0 to 1 of the natural log of 4 minus 3 to the power of x plus 2 times the natural log of 1 plus 3 to the power of x dx. Now, since there's like a sum of integrals, let's just redefine this thing. Let's call this I1. Let's call this I2, just to make our life way simpler. So I1 is nothing but the integral from 0 to 1 of the natural log of 4 minus 3 to the x power dx. Now, you might try all sorts of substitutions, but I'll probably tell you an easy method. So if you remember from my last video, we had the Taylor expansion for the natural log. So the natural log of 1 plus x was the infinite sum from n equals 1 to infinity of negative 1 raised to n plus 1 over n times x to the nth power. Now we want to write this thing, this integrand, in terms of 1 plus some argument. Well, we have a 4 here, so we can multiply and divide by 4 with the hope that something might just cancel off or might simplify. So integral from 0 to 1 of the natural log of 4 minus 3 to the power of x over 4 into 4 dx, because originally there was a 1 in the denominator. To maintain equality, we multiply and divide by 4. Well, the property of natural log is whenever you have things, a product of things inside the natural log, you can just write them as a sum of two different natural logs. So that makes this integral, the integral from 0 to 1 of natural log of, let's just divide this. So 1 minus 3x to the 4th power dx plus, because there's a product in the argument part, so that becomes the sum of two different natural logs. So ln of 4 dx. Well, this is very easy to calculate. This is a constant, it comes out of the integral, and then integration of dx from 0 to 1 is just x evaluated from 1 to 0, which makes it 1 minus 0 or 1. So this in its entirety is just ln of 4. But this, on the other hand, we can write this as an infinite sum, as I have said, the Taylor expansion. So n equals 1 to infinity of minus 1 to the n plus 1 power over n. Now this entire thing, so even the negative will be included in the argument. So we have minus 3x to the nth power divided by 4 to the nth power added with this. Well, now we can interchange the sum and the integral. So we have the sum from n equals 1 to infinity. We can pull all the terms which do not have an x outside of this integral. So minus 1 raised to n plus 1 divided by n, and then we also have 4 raised to n, which does not depend on x, and then the integral from 0 to 1 of well, we can actually also pull out a negative 1 raised to n. So negative 1 raised to n outside, and this just becomes 3 raised to nx dx. This natural log of 4 is untouched. Okay, let's integrate the inside part now. Well, we have n plus 1 plus n because of the power of exponent. So 2n plus 1 over n times 4 raised to n, and the integral of this thing is just 3 raised to nx divided by n times the natural log of 3. Now evaluated from 1 to 0 plus ln of 4. So we have sum from n equals 1 to infinity of minus 1 raised to 2n times minus 1 over, now we can pull this n outside. This becomes n squared times 4 to the power of n, and we can also pull the natural log of 3 outside, and when x is 1, this is just 3 raised to n, and when x is 0 over here, so 3 raised to 0 is 1. That's the natural log of 4. Now we can split this up into like two separate sums, if you will. And before doing that, I would like to remind you that n is an integer, right? Is a positive integer. So 2 times any positive integer is an even number. So negative 1 to an even power is positive 1. So this is 1, and this negative 1 is retained. So we have negative sum from n equals 1 to infinity of let's group terms here. Everything is 3 raised to n and 4 raised to n. We can club them under a common power. 3 by 4 to the nth power all over n squared times the natural log of 3. Fair enough. And now then we'll have a negative sign with a negative 1. But this negative sign and this negative sign will just make it plus. Sum from n equals 1 to infinity of we have 1 over n squared times the natural log of 3. We can bring this 4 to the n on top, making it 1 upon 4 the whole raised to n plus the natural log of 4. Now this is an interesting species, because what does this look like? I mean, some of you who follow my videos a lot might recognize that this inverse square series over here might remind you of the Riemann zeta of 2. But then again, there's also this 3 by 4 which is raised to the nth power while n runs from 1 to infinity. So let me use another page to show you what this really is. Now there is something called the polylogarithm function. It's used a lot in complex numbers and complex analysis and stuff. So the way it's defined is, say you have a polylogarithm of to a base s of say n. So let's call it p. Okay, so it's defined as sum from n equals 1 to infinity of p raised to nth power over n raised to the s power. So in one way of thinking about this is, well, the denominator is a Riemann zeta part. So this might remind you of the Riemann zeta function. But like the numerator is some sort of like a polynomial part. And assuming that the denominator is like a Riemann zeta is correct, because once this say numerator is 1, you just have the sum from n equals 1 to infinity of 1 to the power of n to the s power, 1 to any power is just 1. So just the sum from n equals 1 to infinity of 1 over n to the s power, which is just the Riemann zeta of s. So yeah, I mean that's a pretty nice way of generalizing the Riemann zeta function, the polylogarithm function. So now that I have introduced the polylogarithm function, this is also a polylogarithm. This you can also write as a polylogarithm. So we have a negative as it is, polylogarithm to the base 2, because it's like we have almost like a Riemann zeta of 2 down there, of 3 by 4. If that's in the numerator. So what's in the numerator comes on top, and what's in the denominator comes, you can say it to like a base, divided by the natural log of 3. And same thing over here. So polylogarithm to the base 2 of 1 by 4 over the natural log of 3. That's the natural log of 4. So you can say polylogarithm to the base 2, or you can just call it, whenever you have like a base 2, you can call it the dilogarithm function. And when you have a base 3, you can call it a trilogarithm function. Somewhat like gamma, digamma, and trigamma. Great. So we calculated our first bit I1. Let's go on to I2 now. So we have I2 defined as the integral from 0 to 1 of 2 times the natural log of 1 plus 3 to the x power dx. Now the best part is, since we already have a 1 here, this fits well with our Taylor series expansion for the natural log function. So we can just, without any multiplication division, just simply write this as a integral from 0 to 1 of the infinite sum n equals 1 to infinity of minus 1 to the n plus 1th power over n times 3 raised to nx dx. Okay, we can just interchange the sum and the integral. Sum from n equals 1 to infinity of minus 1 to the n plus 1 over n, the integral from 0 to 1 of 3 to the nx power dx. Integrating this is pretty simple. So sum from n equals 1 to infinity of minus 1 to the n plus 1 over n. Integral of this is just 3 to the nx divided by n times the natural log of 3 as before, evaluated at 1 and evaluated at 0. So let's simplify this a bit. Sum from n equals 1 to infinity of minus 1 to n plus 1 power divided by n squared times the natural log of 3. And then when x is 1, we have 3 raised to nth power. And when x is 0, we have 3 raised to 0, which is nothing but 1. As before, we can just split it into two different sums. So 2 times the summation from n equals 1 to infinity of minus 1 to the n plus 1 power over n squared times natural log of 3. In the numerator, we have a 3 raised to n. Okay, and minus 2 times the sum from n equals 1 to infinity of minus 1 to the n plus 1 power divided by n squared times natural log of 3. Well, look what we have here. I mean, you might recognize this as the Riemann zeta in the base, and then you also have this 3 raised to n, which is like a polynomial term. So you might, if you remember what I explained last time for I1, you might just remember this to be polylogarithm of 3 to the base 2, or the dilogarithm of 3. But let me remind you that our original polylogarithm did not have an alternating part, because in this part, in this I2, we have this alternating sign of alternating negative sign here. So we have a minus 1 to the n plus 1 power. So how do we get rid of this alternating sign? One way to do that is to multiply and divide by negative 1 to the nth power. So say we take like say we multiply and divide by negative 1 to the nth power. Now negative 1 to the nth power times 3 to the nth power, we can just club them up together. We have negative 3 to the nth power, and the entire thing is raised to n. And natural log of 3 times n squared. Now the best part is this term and this term go away. So we have negative 1 to the first power, which is just a negative. It's just a negative. So negative 2 times the sum from n equals 1 to infinity of minus 3 to the n power over n squared times natural log of 3. And don't forget this other part. So this is 2 times the sum from n equals 1 to infinity of minus 1 to the n plus 1 power over n squared times the natural log of 3. Now we can just simplify this. So natural log of 3 is a constant. You can just pull it out. 2 divided by natural log of 3. And what is this exactly? What is this thing? If you've seen my videos, over these few days, you might have already guessed that this is the Dirichlet of 2. And now, since we have no alternating part, we can express this as a dilogarithm. So the dilogarithm of negative 3, right? Because negative 3 is totally inside. It's completely raised to the nth power, divided by the natural log of 3 minus 2 over the natural log of 3, and the value of the Dirichlet of 2 is pi squared over 2n. So let's just finally simplify this. Negative 2 times the dilogarithm of negative 3 divided by the natural log of 3 minus pi squared over 6 times the natural log of 3. This is just your I2, right? And what was our I? It was I1 plus I2, wasn't it? We know that I was I1 plus I2, wasn't it? And we have a value for each of them. So I1 is equal to minus the dilogarithm of 3 by 4 over the natural log of 3 plus the dilogarithm of 1 by 4 divided by the natural log of 3 plus the natural log of 4 minus 2 times the dilogarithm of negative 3 over the natural log of 3 minus pi squared over 6 times the natural log of 3. Now if you see, we can achieve a common denominator by multiplying everything by 6 times the natural log of 3. That's our LCM in the denominator. So finally, we can have minus 6 times the dilogarithm of 3 by 4 plus 6 times the dilogarithm 1 by 4 plus 6 times natural log of 3 times the natural log of 4 minus 12 times the dilogarithm of negative 3 minus pi squared. It's like this is our grand numerator. All of this is just divided by 6 times the natural log of 3. Wow, such a big answer, right? That's maths for you. So, guys, I hope you like this video. Please like, share, and subscribe. Just send it off to any mathophiles you know. And that's it. Have a great day.